Welcome! In this session, we'll dive into the problem number 1649, create sorted array through instructions. This problem challenges us to utilize efficient algorithms for managing sorted arrays dynamically. Let's explore the approaches and break it down step by step. In this problem, we are tasked with creating a sorted array using a series of instructions provided as integers in an array. Each integer in the instructions array represents a number to be inserted into a sorted, non-decreasing array, which starts off empty. The challenge is to calculate the cost of each insertion. This cost is defined as the smaller of two values, the number of elements already in the array that are strictly less than the current number, and the number of elements that are strictly greater than the current number. To compute the total cost, we sum up the individual costs for every insertion. Since the total can grow very large, the result must be returned modulo 10 to the power of 9 plus 7. The input is a list of integers, and the output is a single integer representing the total cost. With this setup in mind, let's look at some examples to better understand the problem. Consider the first example, where the instructions array is 1, 5, 6, 2. We start by inserting the first element, 1, into the empty array, resulting in 1. Since no elements exist before this insertion, the cost is 0. Next, we insert 5, creating the array 1, 5. Here, there is one element less than 5 and none greater, so the cost is again 0. Similarly, inserting 6 into 1, 5 produces 1, 5, 6, with two elements less than 6 and none greater, resulting in another cost of 0. Finally, we insert 2 into 1, 5, 6, resulting in 1, 2, 5, 6. Here, there is one element less than 2 and two elements greater, so the cost is 1. Adding these costs together, the total cost for this example is 1. Now let's examine a second example, where the instructions array is 1, 2, 3, 6, 5, 4. The process begins with inserting 1, producing the array 1 with a cost of 0. Inserting 2 creates 1, 2, again with a cost of 0. Adding 3 results in 1, 2, 3, with no cost as well. Next, we insert 6 into 1, 2, 3, producing 1, 2, 3, 6, with 3 elements less than 6 and no elements greater, so the cost is 0. When 5 is inserted, the array becomes 1, 2, 3, 5, 6. At this point, there are 3 elements less than 5 and 1 greater, so the cost is 1. Finally, inserting 4 results in 1, 2, 3, 4, 5, 6, where there are 3 elements less than 4 and 2 greater, giving a cost of 2. Summing up all the individual costs, the total cost for this example is 3. In the third example, the instructions array is 1, 3, 3, 3, 2, 4, 2, 1, 2. First, inserting 1 creates 1 with a cost of 0. Adding 3 results in 1, 3, again with no cost. The subsequent insertions of 3 into 1, 3, and 1, 3, 3 result in 1, 3, 3, and 1, 3, 3, 3, respectively, each with a cost of 0. Inserting 2 into 1, 3, 3, 3 produces 1, 2, 3, 3, 3, where one element is less than 2 and 3 are greater, for a cost of 1. Adding 4 results in 1, 2, 3, 3, 3, 4, with 5 elements less than 4 and none greater, giving a cost of 1. When 2 is inserted again, the array becomes 1, 2, 2, 3, 3, 3, 4, where one element is less than 2 and 5 are greater, for another cost of 1. Adding 1 produces 1, 1, 2, 2, 3, 3, 3, 4, where no elements are less than 1 and 6 are greater, giving a cost of 1. Lastly, inserting 2 results in 1, 1, 2, 2, 2, 3, 3, 3, 4, with 2 elements less than 2 and 5 greater, for a cost of 0. Adding all these costs together gives a total of 4. Finally, let's consider some edge cases for this problem. If the instructions array contains only one element, there are no comparisons to be made, so the cost is always 0. Similarly, if all elements in the instructions array are the same, the cost remains 0 for every insertion because no elements are strictly less or greater. On the other hand, if the instructions array is sorted in ascending or descending order, the cost for each insertion will be minimal, as all comparisons will occur on one side only. Additionally, because the input size and values can go up to 10 to the power of 5, this emphasizes the need for an efficient algorithm to compute the solution within time constraints. These considerations highlight the importance of optimizing our approach to handle large cases effectively. To start solving this problem, we considered multiple approaches. The most straightforward one is the brute force approach. Here, the idea is to maintain a sorted array as we process each instruction. For every number in the instructions array, we calculate the cost of insertion by counting how many elements are smaller and greater than the current number. This can be done by iterating over the sorted array for each insertion. Once we have the counts, we insert the number into the correct position to maintain the order of the array. However, this approach has a significant drawback. Each insertion and traversal takes linear time, O(n), and since we repeat this process for all instructions, the overall time complexity becomes O(n squared). While this method is simple to implement and works for small input sizes, it becomes computationally prohibitive when the input size grows to larger values, such as 100,000. This limitation led us to consider optimized approaches that can handle larger inputs efficiently. One such approach is to use a binary index tree, also known as a Fenwick tree. This data structure allows us to efficiently count elements smaller or greater than the current number while maintaining a dynamic structure for updates. The Fenwick tree method introduces significant optimizations. First, we compress the values in the instructions array into a smaller range. This is important because the size of the Fenwick tree depends on the range of values, not the number of instructions. By compressing values, we ensure the tree remains compact and efficient. Next, we use the Fenwick tree to perform two main operations for each instruction. First, we count the number of elements less than the current number using a prefix sum query. Second, we calculate the number of elements greater than the current number by subtracting the prefix sum from the total count of elements processed so far. After computing these counts, we update the Fenwick tree to include the current number. This allows the tree to dynamically reflect the state of the processed instructions. The time complexity of each query and update operation in a Fenwick tree is O log k, where k is the size of the tree. For n instructions, the overall complexity becomes O(n log k). This approach is much faster than the brute force method and is also memory efficient. However, implementing a Fenwick tree requires careful handling of value compression and indexing. For comparison, a segment tree can also be used for this type of problem. While it offers similar functionality, it is more flexible in range queries but comes with higher memory requirements and implementation complexity. In terms of complexity, the segment tree approach has a similar time cost of O log k per query and update, leading to an overall complexity of O(n log k). However, segment trees are more challenging to implement and require additional memory for internal nodes, which can make them less practical for this problem. After evaluating all options, we chose the binary index tree, or Fenwick tree, as our preferred strategy. The key insight is that we don't need to maintain the actual sorted array, we only need to count the elements less than and greater than the current number, which the Fenwick tree handles efficiently. Additionally, its minimal memory usage makes it well suited for large input sizes. The value compression step ensures that the tree remains small, even when the input range is large. Compared to the brute force approach, the Fenwick tree offers a massive improvement in performance. While a segment tree provides similar efficiency, its higher memory usage and implementation complexity make it less desirable. The Fenwick tree strikes an optimal balance between speed, memory, and ease of implementation, making it the best choice for solving this problem effectively. The problem asks us to calculate the total cost of inserting elements into a sorted array, where the cost for each insertion is determined by the smaller of two values, the number of elements smaller than the current element, or the number of elements greater than the current element. The challenge lies in maintaining the array in sorted order while minimizing the insertion cost. To solve this, we start by initializing an empty list called sorted_list to keep track of inserted elements in sorted order. We also initialize a variable total_cost to 0, which will accumulate the total insertion cost as we process each element in the instructions array. The algorithm involves iterating through the instructions array and handling each element one by one. For each element in the instructions array, we start by calculating its insertion cost. To do this, we determine the number of elements in sorted underscore list that are smaller than the current element, which we refer to as smaller. Similarly, we calculate the number of elements greater than the current element, labeled as greater. Both counts can be obtained by iterating through the sorted underscore list. Once we have these counts, the insertion cost is the smaller of the two values. This cost is then added to total underscore cost, updating the cumulative cost. After calculating the cost, the current element is inserted into its appropriate position in the sorted underscore list to maintain the sorted order. However, this insertion step is computationally expensive, with a time complexity of O(n), due to the need to shift elements. This process is repeated for all elements in the instructions array. After processing all the elements in the instructions array, the algorithm concludes by returning the total underscore cost as the final result. There are several key insights to consider about the brute force approach used here. First, the time complexity is O(n squared, due to the repeated counting of smaller and greater elements and the insertion operations, which makes it impractical for large input sizes. The use of a sorted list allows us to efficiently calculate relative ordering, but at the cost of expensive operations. The insertion cost calculation ensures that we are always minimizing the cost for each step, but the overall scalability of this approach is limited due to its quadratic growth. While the sorted list simplifies order management, it is inefficient for large-scale inputs, as we will need a more optimized approach to handle larger arrays. Certain edge cases highlight the limitations of this brute force approach. For example, when all elements in the instructions array are identical, the insertion cost for each element is 0 because no elements are smaller or greater. For strictly increasing or decreasing sequences, the insertion cost is always the minimum of 0 or the number of elements already processed. However, the major challenge comes with large input sizes, where the O(n squared) complexity becomes a bottleneck. To address these issues, we can explore optimizations using advanced data structures. A binary index tree, bit, also known as a Fenwick tree, can reduce the complexity of counting smaller or greater elements to O log n. Similarly, a segment tree can efficiently manage range queries and updates. Balanced search trees, like AVL or red-black trees, also offer O log n insertion and search operations, providing a more scalable solution. To better understand the algorithm, let's go through an example with the input array instructions equals 5, 2, 6, 1. When we insert the first element, 5, the sorted underscore list becomes 5. Since there are no elements smaller or greater than 5, both smaller and greater are 0, resulting in an insertion cost of 0. The total underscore cost remains 0. Next, we insert 2. The updated sorted underscore list is 2, 5. For 2, there are no elements smaller, so smaller equals 0, and there is one element greater, so greater equals 1. The insertion cost for 2 is the minimum of these two values, which is 0. Again, the total underscore cost remains 0 after this step. Now, we insert 6 into the list. The sorted underscore list becomes 2, 5, 6. For 6, there are two elements smaller than it, so smaller equals 2, and no elements greater, so greater equals 0. The insertion cost for 6 is the smaller of these values, which is 0. The total underscore cost stays at 0. Finally, we insert 1, but the computation details are not shown here. This example highlights the inefficiencies of the brute force method, especially as the size of the sorted underscore list grows. Optimizations using advanced data structures would significantly reduce the time complexity, making the algorithm feasible for larger inputs. The solution to the problem leverages the sorted list data structure from the sorted containers library to efficiently manage the dynamically sorted array while calculating the insertion cost. First, we define the method createSortedArray, which takes the list of instructions as input. The mod constant is set to 10 to the power of 9 plus 7 to ensure that the final result fits within the problem's constraints. The variable sorted underscore list is initialized as an empty sorted list to maintain the sorted order of elements dynamically. The algorithm iterates through each number in the instructions array. For each number, it determines two counts. 1. Left underscore count is the number of elements smaller than the current number. This is calculated using the bisect underscore left method. 2. Right underscore count is the number of elements greater than the current number. This is calculated as the difference between the size of the sorted underscore list and the index returned by bisect underscore right. The cost for inserting the current number is the minimum of these two counts. This cost is added to the running total cost, which is stored in the cost variable. After calculating the cost, the current number is added to the sorted underscore list to ensure that it remains sorted for subsequent iterations. Finally, the total cost is returned modulo 10 to the power of 9 plus 7 to handle large values and conform to the problem's requirements. This approach is efficient for the given problem constraints because the sorted list operations, insertion, bisect underscore left, and bisect underscore right, each have a time complexity of O log n. This ensures that the overall complexity for processing the entire instructions array is O n log n, where n is the length of the input list. To solve the problem of creating a sorted array through instructions, we use a Fenwick tree, also known as a binary index tree, to officially keep track of counts. First, we define the constant mod to handle large numbers, as the result must be returned modulo 10 to the power of 9 plus 7. Next, we calculate the maximum value in the instructions array, which helps us determine the size of the Fenwick tree. Then, we initialize an instance of the Fenwick tree class and a variable cost to accumulate the total cost of following the instructions. For each number in the instructions array, we calculate two values, left count, which represents the number of elements smaller than the current number, and right count, which represents the number of elements greater than the current number. These are computed using the query method of the Fenwick tree. The cost for the current number is the minimum of left count and right count, and this cost is added to the total. Finally, we update the Fenwick tree to include the current number using the update method. Once all instructions are processed, the total cost modulo mod is returned as the result. The Fenwick tree class is a critical part of this solution. It is initialized with a size parameter, and its internal array, tree, is set to have a length of size plus 1 to account for 1-based indexing. The update method allows us to increment the count of a specific index by a given delta value. It iteratively adds the delta to the current index and then moves to its next responsible index using the formula index plus equals index in index, which ensures efficient updates. The query method computes the prefix sum up to a given index. It starts with a sum of 0 and iteratively adds the value at the current index to the sum while moving to the parent index using index dash equals index in index. This allows us to efficiently calculate the cumulative count up to any index. Together, these methods enable the Fenwick tree to maintain and query the counts of elements in logarithmic time, which is essential for handling the potentially large input size of the problem. We begin with the instructions array 1, 5, 6, 2. First, we initialize mod as 10 to the power of 9 plus 7, an empty sorted list to keep track of the sorted elements, and cost set to 0. Now, for the first number, 1, there are no elements smaller or greater than it in the sorted list, so both left underscore count and right underscore count are 0. Adding the minimum of these to the cost keeps it at 0. The number 1 is then added to the sorted list, making its state 1. Next, we process 5. Here, there is one element smaller than 5, which is 1, so left underscore count is 1. There are no elements greater than 5, so right underscore count is 0. The cost remains unchanged at 0, as the minimum of left underscore count and right underscore count is 0. Finally, 5 is added to the sorted list, which is now 1, 5. Now, we process the number 6. In the sorted list, 1, 5, we find that there are two elements smaller than 6, so left underscore count is 2. There are no elements greater than 6, so right underscore count is 0. The cost remains 0 since the minimum of left underscore count and right underscore count is 0. After adding 6, the sorted list becomes 1, 5, 6. Finally, we process 2. Here, there is only one element smaller than 2, which is 1, so left underscore count is 1. There are two elements greater than 2, which are 5 and 6, so right underscore count is 2. The minimum of left underscore count and right underscore count is 1, so we add 1 to the cost, making the total cost 1. After adding 2, the sorted list becomes 1, 2, 5, 6. The final output of the cost modulo mod is 1. In the next example, the instructions array is 1, 2, 3, 6, 5, 4. We again initialize mod is 10 to the power of 9 plus 7, an empty sorted list, and cost set to 0. Starting with the first number, 1, there are no smaller or greater elements, so both left underscore count and right underscore count are 0, and the cost remains 0. Adding 1 results in a sorted list of 1. For the number 2, there is one smaller element, which is 1, so left underscore count is 1. There are no greater elements, so right underscore count is 0. The cost remains 0, and the sorted list becomes 1, 2. For 3, we find two smaller elements, 1 and 2, making left underscore count 2. There are no greater elements, so right underscore count is 0. The cost remains unchanged at 0, and the sorted list updates to 1, 2, 3. The number 6 results in left underscore count of 3, as all elements in the sorted list are smaller, and right underscore count of 0. The cost remains 0, and the sorted list becomes 1, 2, 3, 6. Next, for the number 5, there are 3 smaller elements, 1, 2, and 3, so left underscore count is 3. There is one greater element, 6, so right underscore count is 1. The minimum of these is 1, so we add 1 to the cost, making it 1. After adding 5, the sorted list becomes 1, 2, 3, 5, 6. Finally, for the number 4, there are 3 smaller elements, 1, 2, and 3, so left underscore count is 3, and 2 greater elements, 5 and 6, giving a right underscore count of 2. The minimum is 2, so we add it to the cost, making the total cost 3. Adding 4 results in the sorted list, 1, 2, 3, 4, 5, 6. The final output of the cost modulo mod is 3. In the final example, the instructions array is 6, 5, 4, 3, 2, 1. Again, we initialize mod as 10 to the power of 9 plus 7, an empty sorted list, and cost set to 0. Starting with 6, there are no smaller or greater elements, so both left underscore count and right underscore count are 0, and the cost remains 0. Adding 6 results in a sorted list of 6. For 5, there are no smaller elements, so left underscore count is 0, and one greater element, 6, so right underscore count is 1. The cost remains 0, and the sorted list becomes 5, 6. For 4, there are no smaller elements, so left underscore count is 0, and two greater elements, 5 and 6, making right underscore count 2. Again, the cost remains 0, and the sorted list updates to 4, 5, 6. For the number 3, there are no smaller elements, so left underscore count is 0, and 3 greater elements, 4, 5, and 6, giving right underscore count of 3. The cost remains unchanged at 0, and the sorted list becomes 3, 4, 5, 6. Now, we process the number 2. There are no smaller elements, so left underscore count is 0, and 4 greater elements, 3, 4, 5, and 6, giving a right underscore count of 4. The cost remains 0, and the sorted list updates to 2, 3, 4, 5, 6. Finally, for the number 1, there are no smaller elements, so left underscore count is 0, and 5 greater elements, 2, 3, 4, 5, and 6, making right underscore count 5. Again, the cost remains 0, and the sorted list becomes 1, 2, 3, 4, 5, 6. The final output of the cost modulo mod is 0. Here, we're analyzing the time complexity of the solution using the sorted list data structure. First, the insertion operation in the sorted list uses binary search to find the correct position and then inserts the element, which takes O, log, n, time, where n is the current size of the list. Next, when we calculate the counts of elements smaller or greater than the current number using the bisect underscore left and bisect underscore right methods, each of these also uses binary search, making them O, log, n, operations as well. Since we perform these operations, 2 binary searches and 1 insertion, for each element in the instructions array, the time complexity per instruction is O, log, n. This provides the foundation for the overall time complexity analysis. Now, looking at the overall time complexity of the algorithm, let m represent the total number of elements in the instructions array. For each of these m elements, we perform operations that take O, log, n, where n grows from 0 to m as we process the instructions. In the worst case, n equals m, so each operation effectively takes O, log, m. Summing up the costs across all m instructions gives us a total time complexity of O, m*log, m. Shifting to space complexity, the sorted list stores all elements from the instructions array, and in the worst case, where all elements are distinct, it grows to size m. This results in O(m) space being used by the sorted list. Additionally, the algorithm uses constant auxiliary space for variables like mod, cost, left_count, and right_count, which consume O(1) space. Binary search operations like bisect_left and bisect_right are performed directly on the sorted list without requiring extra memory. Therefore, the final space complexity of the solution remains O(m). In comparison to a naive approach that iterates through the sorted list to count elements smaller or larger than the current number, the optimized approach is significantly faster. The naive approach would require O(n) time per instruction, leading to an overall time complexity of O(m squared, while the space complexity remains O(m) due to the storage of the sorted list. The optimized solution, by leveraging binary search for counting operations, reduces the time complexity to O log n per instruction. This improves the overall time complexity to O(m log m, making it much more efficient for larger inputs. The space complexity remains unchanged at O(m), as the sorted list still needs to store all elements. When analyzing best, worst, and average cases, we observe that the time complexity is consistent across scenarios. In the best case, where the instructions array is already sorted, insertion and counting still take O log n time. In the worst case, where the instructions array contains distinct and randomly ordered elements, the sorted list grows to its maximum size, but the time complexity remains O(m log m). For the average case, the performance is similar to the worst case, as the operations involve the same O log n complexity per instruction. To mathematically validate the time complexity, consider that for each of the m elements in the instructions array, we perform two binary searches in one insertion, each taking O log n. Combining these operations gives us O log n per instruction. As n grows from 1 to m, the sum of all operations becomes O log 1 plus O log 2 plus O log m, which simplifies to O(m log m, as log m dominates the sum. The space complexity, determined by the size of the sorted list, is O(m) in the worst case. Therefore, the final time complexity is O(m log m, and the space complexity is O(m). When solving this problem, there are several common mistakes to watch out for. First, if you're implementing a binary search tree or related structures like Fenwick trees or segment trees, make sure to handle duplicates correctly and account for edge cases that can cause the tree to become unbalanced. An unbalanced tree can significantly degrade performance, reducing your algorithm to O(n squared in some cases. Proper balancing and support for duplicate keys are critical. Second, avoid naively sorting the array for every insertion in a brute force approach. While it might work for small inputs, this method is highly inefficient with a time complexity of O(n squared log n, and will fail for larger constraints. Instead, focus on optimizing the process by using binary insertion techniques. Another critical area where mistakes occur is in the cost calculation. It's easy to mix up indices or forget to reset counters when calculating the cost based on smaller and greater elements for each insertion. Take extra care to ensure your logic is precise and avoids off-by-one errors. Finally, if the problem requires modular arithmetic, such as taking results modulo 10 to the power of 9 plus 7, forgetting to include the modulo operator in intermediate calculations can lead to incorrect results or even integer overflows. Pay close attention to this requirement when it's specified. Now, let's look at a few more key points. Ignoring the problem's constraints and failing to optimize accordingly is another common pitfall. For example, using a brute force solution when the input size is large will almost certainly exceed the time limit. Tailor your approach to the constraints and choose efficient methods when necessary. From an interview perspective, recognize that this problem aligns with patterns like order statistics or range queries. Data structures like Fenwick trees, segment trees, or binary index trees are commonly employed to efficiently manage insertion and cost calculations. Be prepared to discuss the trade-offs between space and time complexity when using advanced structures. While these data structures offer faster query and update operations, they also require additional space for pre-processing. Interviewers often appreciate a discussion of these trade-offs. Additionally, always address edge cases, such as handling duplicates, empty arrays, or arrays with a single element. Finally, communication is crucial when explaining complex data structures. Clearly articulate your thought process, and if possible, use diagrams or examples to demonstrate how updates and queries are performed. This helps convey your understanding effectively. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 315, count of smaller numbers after self, is a similar problem that involves tracking smaller elements and often uses binary index trees or a divide-and-conquer approach. LeetCode 493, reverse pairs, also focuses on range queries but with a specific emphasis on counting pairs that meet certain conditions. LeetCode 327, count of range sum, takes this a step further by introducing range sums into the mix. Finally, LeetCode 307, range sum query mutable, serves as an excellent foundational problem for learning about Fenwick trees and segment trees. In terms of alternative approaches, Fenwick trees, also known as binary index trees, are highly efficient for managing dynamic prefix sums and updates, with a time complexity of O(n*log en). However, they do require additional space. Segment trees offer similar flexibility for range queries and updates but demand even more space than Fenwick trees. Another option is the merge sort with count method, which calculates insertion costs during the merge phase. This method has a time complexity of O(n*log n) and is a space-efficient alternative, though it can be harder to implement dynamically. For smaller inputs, brute force remains a straightforward way to validate the correctness of optimized solutions, even though it doesn't scale well for larger datasets. Great job! We've successfully reviewed the problem and its solution. Remember, dynamic array problems often require advanced data structures for efficiency. Keep practicing and refining your skills. Thanks for watching. Don't forget to subscribe for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!